Hi, folks. Hope you're all well, considering the circumstances we find ourselves in right now. Um, JL asked if I'd be willing to sit down and explore with you some of the research topics that my group works on here at the University of Hull and what we've been doing over the last decade or so. And in particular, if I would be willing to delve into sort of the dark arts, if you like, that underpin the sorts of simulations of galaxies that you see on your screen right now. So what I've done is pulled together sort of 45 minute overview of the history of galaxy formation simulations. Hopefully, if nothing else, to distract you from the ongoing coronavirus news stories that probably fill your news feed every hour on the hour, as it does for mine as well. So hopefully, you'll pick up something new that you haven't seen before. And if you have any follow up questions, we can talk about it offline. We can run a small little group chat if you have any, or just fire off some questions via email or through Canvas in an asynchronous way, and I'll get back to you. And hopefully, when all this calms down, we can actually sit down over a pint or something and chat a little bit more about some of the details that I'm going to touch on here. So let's kick off. I guess if I'm somewhat flippant about it, people in my field who work on these galaxy formation simulations, we've sort of adopted the title of Galactic Archaeologists. Maybe not quite as exotic and romantic as Harrison Ford and Indiana Jones, etc. But it's a moniker that's a fair and realistic one in the sense that what we're trying to do with both observations and simulations of galaxies is literally to try to mine the fossil record that you see in the not only the structure, the shapes of galaxies, the chemical fingerprints that are encoded in the stars and the gas clouds throughout the galaxies, as well as the kinematics, the motions of the stars and the gas clouds throughout the galaxies. Now, whether you're approaching it the way I do from a high performance computing perspective, what I try to do is observe my simulations in as faithful a way that reproduces the way in which observers do exactly the same thing with telescopes, and ultimately that is uh, the bridge that we try to cross if we're trying to bring those two different communities, the observers and the theoretician, the modelers, the simulators together. And ultimately, it is to do exactly the same thing as you see there in those panels. It's looking at structure, chemistry, and kinematics, whether they're real ones or simulated ones. And ultimately, it's trying to pin down the maths and the physics that shape the formation and evolution of galaxies. Now, it sounds simple enough, but before you can do that, though, you actually have to have some simulations that at least look like real galaxies. And for most of the people in my field, that means looking like real spiral galaxies or real disk galaxies like the Milky Way. The nearest big galaxies to us, not counting the Milky Way, would be the Andromeda Galaxy. Um, and it's more or less a sister twin galaxy to the Milky Way. They're classical grand design late type spirals, as they're referred to. And so it begs the question, can we actually get simulations that at least look like real disk galaxies? If we're going to try to underpin the physics and mass that shape those things, you need to have something that at least looks like a real galaxy. The problem is, if you look back over the literature over many decades, and I'll go through that in a whirlwind way in a few minutes, the problem is that until about maybe 10 years ago at best, most of the simulations of, say, spiral galaxies or late type galaxies or disk galaxies, I'll use the terms sort of interchangeably, look more like the panel you see there on the left. You can see that there is a disk down there in the center with a dust lane cutting across it, but you can also see there's an enormous amount of light tied up in sort of a spheroidal component or a bulge component or a halo component. Again, you'll hear these terms interchangeably. The problem is most late type galaxies, like our Milky Way, like Andromeda, look more like the one on the right, where the vast majority of the light is tied up in the disk component. In this particular example, there's a tiny little um, nuclear component in the center. Our Milky Way, maybe 10% of the light might be tied up in that central spheroid bulge component. Similarly with Andromeda. So the classical grand design spirals are really disk dominated. They're not like the one on the left where it's more spheroid dominated. And the problem in all of this is that inside of a simulated galaxy, you are working at a resolution scale for the most part inside of your simulation, which is maybe 6 orders of magnitude, 7 orders of magnitude away from the sorts of things that you can see there by eye, bright stars, small gas clouds. The resolution that you need to simulate those self-consistently inside of the galaxy is just something that we just can't do, both hardware or in software, at the same time as simulating the gross properties of the galaxy as a whole. This is all called broadly subgrid physics. It's all of the gory physics that you cannot resolve at the level that your simulation is running at. And I'm going to touch on that and how we handle the fact that we can't resolve things like star formation and the feedback from exploding stars at the same time as we do the dynamics of the galaxy as a whole. And ultimately, that is the sort of physics, that subgrid physics, that shapes whether you're going to get something which looks like the one on the left, a bulge-dominated, spheroid-dominated galaxy, or the one on the right, which is a disk-dominated galaxy. And this has really been the problem that has plagued us over the last 50, 60 years or so since this field sort of started going. And like I said, it's only really in the last decade that we've made progress in getting things that look more like the galaxy that you see there on the right. So I said I would do a whirlwind tour of the history of galaxy formation simulations. So the place I'm going to start is not actually with a simulated galaxy. It's with a telescope. It's called the Leviathan of Parsonstown. It was built in Ireland at Burgh Castle by William Parsons in early 1840s. It's a beautiful piece of equipment. Until maybe about 70, up to about 70 years ago, 80 years ago, it was the largest optical telescope in the world, about 2 meters in diameter. One of the mirrors is still at the Science Museum in London if you want to go see it. It's a monstrosity of mechanical winches and pulleys to move this thing around. It's not like the modern telescopes in any way, shape, or form. It was built in particular to address a hot debate at the time in the sort of early part of the 1800s, something called the nebular hypothesis, which really boils down to there were two camps. There was Parsons and his cohort, who believed that if you built a big enough telescope and pointed it at some of the fuzzy blobs that people had identified in the sky, they would actually resolve into things that had coherent, regular structure. It was simply a matter of resolution. And then there were those on the other side of the camp, John Herschel and his team, who believed that it didn't matter how big your telescope was, how good your resolution was, these things would remain unresolved, perhaps because of distance. Now, with hindsight, we can look at this and both camps are right. When you point at fuzzy blobs in the sky, some of them do resolve into nice, coherent, grand design spirals with structure, whereas some of them are either distant or sort of just gas clouds and dust clouds that, no matter how you resolve them, still look unresolvable in that sense, with at least not possessing any sort of coherent structure. And as an aside, this telescope, which you can go visit, was one of the last things that Patrick Moore worked on before he passed away, was renovating and bringing it back up to scratch. Up until, I guess, early 1900s, it was actually responsible for discovering and cataloging at the time about 10% of these fuzzy blobs, things that were part of what's called the NGC catalog. So 10% of that catalog, which is made up of tens of thousands of galaxies, were actually uncovered painstakingly by Parsons and his family and friends. over a number of decades, working at this site in Ireland, which you can see from the panel on the left. It's obviously not the best site in the world for sighting an optical telescope, but they still discovered an enormous amount of fascinating targets in the sky. And even now, this NGC catalog, which has got, I don't know, 50,000, 100,000, I'm not sure how many cataloged objects are in there, but 3% of those objects were actually discovered and first identified by Parsons and his team using this Leviathan in Parsons Town. So one of the first things that he did in 1845 when this telescope was built was he pointed at one of these well-known fuzzy blobs. It's called the Whirlpool Galaxy now, or M51. And that's the sketch that you can see. And so his great discovery at the time, 1845, was that the first fuzzy blob that he pointed at actually did resolve into something with coherent structure, with spiral arms. And so, at least at first glance, based on one object, he felt that he had won the debate with Herschel. Now, again, you could have pointed at another fuzzy blob and it wouldn't have resolved into something with coherent structure. So again, in hindsight, when we look back 170 odd years later, this is not a particularly startling discovery. In some sense, we sort of take it for granted now. But at the time, that was an exciting discovery that these things can be resolved into things with coherent structure, at least some of them. And if you take a look and compare it with what you see today with Hubble Space Telescope M51, you can see that Parsons had captured the essence of what this Whirlpool galaxy looks like. Now, really, what is much more exciting, though, rather than the fact that you could actually see coherent structure in here, really the greater discovery, though, is that little thing that he's drawn up there in the top left panel there. This other little bright blob, and it's a satellite galaxy, if you like, of M51, which is interacting with it, and it's actually drawing because of the tidal interaction, gravitational interactions going on through this, the tidal forces. It's stretching out, pulling out the part of the spiral arm towards the satellite galaxy, and so this was really the first identification and recognition, if you like, that galaxies are not sort of isolated islands, but that they do evolve and assemble through these things. You'll hear people talk about interactions and mergers and accretion, harassment. They're all different terms that are used to capture the essence that galaxies are effectively sort of living, breathing things that are continually growing and assembling. That is something that 175 years later is still very much a hot topic within the field of astronomy and astrophysics. What is the maths and physics that shapes this assembly, accretion, harassment, hierarchical merging, etc., etc.? So if Parsons had sort of stepped back and sort of thought about this for a second and looked at what he'd actually drawn, he may have asked the question, well, what ultimately is the effect of this satellite as it's interacting? I can see from what I've sketched here that it's drawn part of the spiral arm out here. But what is the ultimate effect of what this interaction is? What is it going to lead to downstream? Now, this is a relatively straightforward thing for us to answer nowadays. We do this using various modeling tools, and we can do it. You can do it on a supercomputer if you like, where you take a galaxy, or in this case, two galaxies that you can see interacting with each other, and representing them with millions or billions of particles. And these are what we call an n-body simulation, where you represent the galaxy as a family of n particles, and those particles include stellar particles, includes dark matter particles, includes gas particles. Again, it's dead easy for us to do this now using Viper here at Hull Uni, but it's not even that. You can do it on your smartphone. You can download apps to run these sort of n-body simulations, and you would be able to answer that question that Parsons didn't really ask when he did that sketch, is, what is the ultimate fate of this interacting system? But even though he didn't ask that question, the actual underlying physics was well known. It had been known since the time of Newton. was no particularly tricky physics involved in it. It really just comes down to the inverse square law of gravity. Now, it also involves some fluid dynamics, which I'll come back to in just a second. Now, doing this on a smartphone or Viper or any other supercomputer wasn't really an option in the 1840s. And in that sense, the field kind of just languished for sort of 100 years or so. And we normally think of the first sort of computational simulations of galaxy interactions, n-body simulations, as this classic paper that's on the screen right now from 1972 from a pair of brothers, Toomre and Toomre. It's one of the most cited papers in all of science, not just in astronomy and astrophysics. It was the first real systematic study of interacting systems. It's a very lengthy paper, very elegant, very beautiful, representing two interacting systems with 120 particles each. Again, no other physics other than the inverse square law of gravity. And then throwing these two systems at each other at different speeds, different passages of closest approach, different mass ratios, different orbital configurations, and viewing them from different angles to try to recover things that you actually observe in nature. In this case, just showing you one example of one of their simulations, which was to recover this system called the MaGICC. Now, that's what we normally think of as the beginning of n-body simulations of galaxy formation, galaxy interactions, this classic paper from 1972. People who are in the know, real aficionados, actually will go back 12 years earlier to really a little-known paper, largely because other than the abstract, the paper was only in German for a number of years, so it didn't reach the full international readership, if you like. But again, it's a beautiful paper from Sebastian van Horner, where rather than using sort of 120 particles to represent a galaxy, this was the very first simulation using a computer. And if you read the fine print on there, you can see that he ran 4 different simulations with 4, 8, 12, and 16 particles to represent the system. Here it's not a galaxy, it's a globular cluster, but the essence is the same. Really is just the inverse square law and tracking the motion of those 4, 8, 12, or 16 particles. This is really, in some sense, sort of the first resolution study to see if the results, how well do they depend on the resolution of your simulation. Again, the dynamic range is not huge in going from 4 to 16 particles, but it really was sort of the first systematic test of the numerics, if you like, even though it's small numbers. Beautiful, but very little known paper. But even that one from 1960 is not really the beginning of the n-body simulation game. It actually goes back to 20 years earlier, 1941, and that is about 7 years before the invention of the computer. So you might wonder, how did this galaxy simulation paper actually come about when computers didn't actually exist at that point in time? That's a really prescient, beautiful paper from Erik Holmberg in Sweden at Lund Observatory, who recognized he didn't have a computer to play with, so he wasn't going to be able to do the motion of the particles that represent the galaxy self-consistently, tracking their gravitational interactions. But what he did recognize was that light and gravity both obey the exact same physical law, just the inverse square law. So what he did was take his lab and put black paper all around it, so he block out all the light. Down on the floor of the lab, sort of, I think was something about 20-25 square meters or so in the footprint of the lab, and he placed, if you like, 2 galaxies down on the floor, but these were galaxies comprised of 37 light bulbs each, about a meter or so across in diameter. So it's not as many particles, if you like, as were in the Toomre and Toomre paper 30 years later, where they had 120 particles to represent a galaxy. Here they've only got 37 particles, but they were clever. They laid out these 37 light bulbs on the floor for each galaxy. There's more towards the center than the outskirts, so that represents the, if you like, the exponential density profile of galaxies, where there's more light in the center than there is in the outskirts. And what he systematically did over months and months, these simulations, if you like, took to run, was that he would go to one of the light bulbs, remove the light bulb, replace it with a photocell, and he would face the photocell in one cardinal direction and measure the current through this galvanometer, looking at all of the light bulbs when it was pointed in one particular cardinal direction that photocell could see. And then he'd rotate it 45 degrees, measure the current, take a look at how many light bulbs he could actually see, then rotate it another 45 degrees, and he would go all the way around 360 degrees, and then put the light bulb back, go to the next light bulb, replace that one with a photocell and galvanometer, go through the same process again. And wherever the current was highest, as he rotated the photocell around, that would correspond to where the gravitational tug would be the strongest, because again, light intensity and gravity both go as an inverse square law, so we can just use light as a proxy for gravity. That would allow him to adjust the position of the light bulb in response to the gravitational tug, or the light intensity, if you like, and systematically walk his way around each of the 37 light bulbs in each of the two galaxies and track the gravitational interaction that way through the intensity of light. And Holmberg did more or less what Toomre and Toomre did, was a systematic study, putting the galaxies down on the ground and then moving them towards each other, having different passages, closest passage, what we call the pericenter, different hyperbolic orbits, different parabolic orbits. He could vary the voltage through the light bulbs in one of the galaxies to either make it brighter or fainter, and that would mimic sort of a dwarf galaxy as opposed to a giant galaxy, or what we call different mass to light ratios. And what he found, he could have the galaxies spinning in the same direction as the orbit was between the two systems. So you'd have coupled angular momentum, what we call a prograde interaction. You could have the galaxies spinning their spin angular momentum in the opposite direction of the orbital angular momentum of the interaction. We call it retrograde interaction. Both of the examples are shown there on the screen there in cartoon form. And he went through and found, what were the best configurations if you wanted to draw out long tidal features, or if you wanted to have a bridge of material appear between two interacting systems. And what he found, the conclusions are sort of written there with some quotes there under the results on the left, are exactly what you would find today if you move forward, 80 years in time. It doesn't matter whether you are using 37 light bulbs to represent your galaxy, or using nowadays tens of billions of particles to represent your galaxy. The conclusions are exactly the same. They haven't changed in 80 years. It's an incredible paper that didn't get a lot of attention when it came out, but has now sort of gotten belatedly the attention that it deserved. Really is the first n-body simulation, and does predate the invention of the computer by 7 years. Now, all I've really talked about in terms of the physics inside of these simulations is the inverse square law. Again, it's very easy. It's very easy to code. Now, when you start to move from 37 light bulbs or 120 particles to represent your galaxy to thousands or tens of thousands of particles to represent your galaxy, you can play this game of summing over each individual particle's gravitational effect on its surrounding particles. It starts to get a bit unwieldy as the numbers of particles grow. You can't do this ad infinitum eventually, because the timing goes as n squared. So as you double the particle number, it's 4 times as long to actually run the simulation. It becomes unwieldy when you moved from hundreds or thousands of particles up to millions or billions. It becomes impossible to do this. And it's a little bit more complicated than just summing over the inverse square law of all of the particles. Really, and without belaboring it, what it comes down to is is solving what's called the collisionless Boltzmann equation, which is tossed up in front of you there, which is the time evolution of phase space. So phase space is denoted by F there, and phase space is basically the 7-dimensional phase space of position in XYZ and velocity in XYZ and time. So it represents that distribution of phase space of all of the particles. And the only other term that sort of would note in there is that capital phi that represents the gravitational potential, and that's solved using Poisson's equation, that second equation, which is there. So really what it really boils down to is you use a collisionless Boltzmann equation to get the positions of all of your particles given that potential phi. Having adjusted the positions of the particles given that gravitational potential, now everything's in a slightly different position, so you have to recalculate the gravitational potential using Poisson's equation. Having changed the potential, it means that the particles will also adjust a little bit, so that you trade off between solving the collisionless Boltzmann equation to adjust the positions, and then Poisson's equation to recalculate the potential, and then you cycle around back and forth between solving the Boltzmann equation and the Poisson's equation. And this works great for a large chunk of the universe. Roughly about 85% of the matter in the universe is dark matter. It's a whole other topic of discussion. We don't know what it is. We know it's there. We can sense it. We can feel it. We can see its gravitational influence on things around us. And like I said, it's 85% of the matter in the universe, but ultimately at its heart is just the inverse square law. It doesn't care about electromagnetism, doesn't care about the strong force, weak force. It's just gravity. And so the fact that 85% of the matter in the universe only cares about the inverse square law of gravity, it's probably not shocking that models do actually, with nothing else other than that inverse square law, you can actually get things that look like our universe. So if you look at simulations on the largest scales, where you take the initial conditions, again, won't go into the details, but we use the cosmic microwave background, sort of the embers that are left over from the Big Bang. We use those subtle temperature distribution from point to point and the cosmic microwave background as the initial conditions, and then basically just take those initial conditions and turn on the inverse square law. If we do that, let it run for 13.5 billion years, what you get is that rotating sort of 3D cube that you see there, which is this sort of web-like cosmic web of the universe. You've got regions which are underdense or voids. You've got regions which are high density with clusters that meet where filaments come together. And if you go through and take various high-order statistical measures of the topology of that structure that you see, it actually, statistically looks very much like what you see in nature, which is the figure that you see on the left is a distribution of galaxies through from the 2DF Galaxy Redshift Survey. The main point to take from that, again, is that for large-scale structure, on the largest scales, you don't need anything other than cosmic microwave background and the simplest, inverse square law, and you get a universe that looks like what we see today. So that's great. On the other side, what happened when you zoom into some of those bright spots in that simulation where you have individual clusters and individual galaxies, the models started to break down. So those, for example, the first attempts to use just the inverse square law to get things that look like, say, our Milky Way or the Andromeda Galaxy failed. What we ended up getting were things that look like what we call elliptical galaxies. So you can see that little box with the green tick. This particular simulation, which was classic work from about 40 years ago from Simon White, all of his simulated galaxies are fairly featureless, structureless. They look like the fuzzy, boring, homogeneous blobs called elliptical galaxies. He didn't get anything that looked like grand design spirals like the Milky Way or Andromeda. So a lot of, again, this is only 40 years ago, but the immediate thought came to be, The only thing that we've actually done so far is the inverse square law, and like I said, that's great for 85% of the matter in the universe. The problem is that 85% we can't see directly. You can't put a telescope on and point towards it. The stuff that we actually see with a telescope is the normal matter, what we call the baryonic matter, the stuff we're made out of. That only comprises 15% of the matter in the universe. And unfortunately, to model that 15%, it's not just the inverse square law, otherwise it would be dead easy. It means you have to put in gas physics. And gas physics is basically fluid dynamics, just a really, really dilute fluid. So it enters you into the realm of hydrodynamics and fluid dynamics. And that's really where the field has spent the last sort of 40 years working on, is implementing fluid dynamics coupled with the inverse square law that covers the pure and body side of things. So if you boil it down to equations, the already introduced the fact that the gravitational and body simulations are just comprised of this collisionless Boltzmann and Poisson equations to get the positions of the particles and then calculate the gravitational potential given those that phase-space distribution of points. That's pretty dead. It's dead easy to do. You can do it in a computer, and you can run with billions and billions of particles because the physics is so simple. As soon as you actually want to model the stuff you can actually observe, that means gas dynamics, and that's where the laws of fluid dynamics come into play. And what that means inside of the codes that we employ, there are lots of lots of codes out there. Particle-based approaches to hydrodynamics or grid-based approaches to hydrodynamics. Again, details don't really matter. Underlying whichever approach you take are these three pretty straightforward differential equations that are coupled: continuity equation, Euler equation, and energy equation. Really, what they boil down to, they're just conservation laws of mass, momentum, and energy, respectively. I'm just going to say a couple words about in the next slide about the energy equation, because that's ultimately the one which is really the important one. Unlike, say, dark matter, which, like I said, doesn't care about electromagnetism, strong or weak forces. Dark matter doesn't heat up, it doesn't cool down. Gas is obviously different. It can heat up, it can cool down. And that energy equation, which is the rate of change of the thermal energy, which is the little u, you've got that term on the right, that big capital lambda. This is where all of the gory physics that goes into all of the cosmological and galaxy formation simulations that are worked on around the world today, and it's a huge industry. Everything is hidden inside of that one term. This is where all of what I referred to at the beginning is subgrid physics. A lot of the stuff that we cannot resolve inside of these simulations are hidden inside of that term. That's where all of your energy sources and energy sinks are hidden away. You'll often hear, particularly the hottest topic is feedback, energy feedback from exploding stars, which is ultimately the primary source of energy for heating up the interstellar medium, heating up the gas. Now, every time a star explodes, and it happens in the Milky Way about every 10 years or so, you get an exploding star, a supernova goes off. It dumps 10 to the 44 joules, 10 to the 51 ergs of energy into the surrounding interstellar medium, which is, again, an enormous amount of energy. And one of the decisions that we have to make when we're running these sorts of simulations is, how do you distribute that energy to the surrounding interstellar medium? We don't resolve the physics at the level that we do in nature. Again, you would have to go 6-7 orders of magnitude down in resolution to actually resolve individual supernova events. We simply can't capture that in these galaxy formation simulations. It's just not feasible. So what sort of decisions do we make on that energy? Do we assume it all goes into thermal energy and just heats up the surrounding gas, which causes the bubble around and percolate more? Do you put it into kinetic energy and give a forcible kick to the surrounding gas particles and push them around? How do you choose how far out do you allow that energy to distribute? Do you just take the nearest gas particles, the nearest 4 particles, nearest 32 particles? Do you include the effects of magnetic fields. If you look in a galaxy like the Milky Way, the energetics of the interstellar medium is split more or less equally between the turbulent energy from exploding stars, magnetic fields, and high energy cosmic rays. There's what we call equipartition of energy. Most simulations, almost all simulations that have been done to date, ignore magnetic fields and cosmic rays, which could be an important heating source that have been neglected. Do you include the fact that before a star explodes, it pumps out a lot of high energy photons that could heat up the surrounding interstellar medium, or do you just ignore it and put it all into explosion energy? Do you include the effects of supermassive black holes, which can use their jets to heat up some fraction of the interstellar medium? There's a whole lot of decisions that you have to make in terms of what those energy sources and sinks are going to be, how you characterize them when you're working at resolution scales that are a million times greater than where these things actually act in nature. So this is really the dark art of simulations, this subgrid physics. And it's perhaps not shocking to hear that there isn't one correct solution because you're working at many orders of magnitude away from where these things are really happening. There are some degeneracies in the different approaches. I'll show you some of the successes and failures over the last sort of 10 to 20 years in this field and where we stand today. One of the big breakthroughs was actually this paper from 1977, so only 40 odd years ago. It's called a smooth particle hydrodynamics (SPH) approach to hydrodynamics and fluid dynamics. Now, astronomers did not invent fluid dynamics. It certainly predates astronomy and astrophysics. But what astronomers did do was find a very clever, elegant, accurate, and very fast way to solve those equations of fluid dynamics by discretizing the gas up into particles. And it's called SPH. It was a pair of astronomers who were working in Cambridge at the time. Their interest was basic astronomy. How does, fundamental science, how does energy get from the hearts of stars and carried out through the atmosphere? And they designed this algorithm SPH that allowed them to make some very powerful insights into how energy propagates through stars. And they weren't thinking about the broader applications, but what did become clear after that was the industry did recognize that this new particle-based approach to hydrodynamics had applications way beyond sort of the fundamental science that Gingold and Monahan had in mind. And you can look across all kinds of different sectors, from aerospace engineering to, up there in the top right, biomedical engineering. You're seeing a blood flow through an artery in an artificial heart. You see the turbulence of the blood as the valve opens and closes. Structural engineering in the bottom left, working out stresses and strains on an oil rig. Automotive engineering in the bottom right. You've got things like bottom right there, you've got work from one of my students who works at the World Bank in the Natural Disasters Division, doing simulations of countries come to the World Bank and ask them to do a risk analysis when they want to build, a hydroelectric dam upstream somewhere. So he plays around with placing dams in different locations. He can change the soil content, put different ground cover, moss, grass, trees in different places, rocks, various shunts to try to minimize damage in case of a catastrophic failure of the dam. Or in the bottom left there, we're looking at some work done at Siemens on the design of turbine blades for renewable energy. All of these are using smooth particle hydrodynamics, SPH. Now, again, SPH is not the only approach that is used in all of these industrial applications. There are grid-based approaches as well, and finite element analysis. But SPH has been adopted alongside all of those, and it's one of those things that, when I'm in discussions with funding councils and governments about some of the application side of astronomy and astrophysics, this is one of the things that I do like to point out, that basic fundamental research into stellar astrophysics led to SPH, which has had these knock-on influences in all these different industries. So let's now look at what happens when you take the inverse square law of gravity and you couple with the laws of fluid dynamics. So what was the hope here? Well, the hope was that we were going to get, if you're someone like me, one of these galactic archaeologists who's interested in trying to pin down the physics that shapes late type spirals like the Milky Way and Andromeda, this is what we were hoping to get, these sort of big, thin disks. When you view them sideways, they're quite thin. Small bulges in the center where maybe, a few percent, 10% at most of the light is tied up in that spheroid component in the center. And, you get these nice grand design spiral arms. That was the hope. Is what we couldn't get when we just used the inverse square law of gravity. The hope was when we put in the hydrodynamics that shape the gas, which ultimately that gas is what turns into stars, that these are the sorts of galaxies that we would get. So the very first simulations weren't done, and it was only about 30 years ago, 1992. Neil Katz was the first one to do this, and then shortly thereafter Steinmetz and Mueller. So the field really only got started coupling inverse square law with fluid dynamics 25 years ago. And what they ended up getting was things that did look like they weren't elliptical galaxies, they are disk galaxies. If you turn them sideways, like the panel on the right there, it's thinner. If you view them face on, they're sort of round. They are rotating, so they are disks, but they're sort of stubby, thick disks. They have a large spheroid component attached to them, and there's nothing in the way that looks like beautiful grand design spiral arms. So we did actually get disk galaxies. That was the positive, but we didn't really get anything that looked a whole lot like the Milky Way or Andromeda. It was recognized pretty early on what the problem was, and they basically were too concentrated. What happens was, gas is different than, say, particles, like star particles and dark matter, which only feel gravity. Gas feels gravity, of course, as well, but it also dissipates energy. It's you can heat up the gas, you can cool it down, it can rub together and lose energy. That causes it to lose angular momentum. And unless you have a balancing heat source that keeps it sort of propped up, it will lose that angular momentum catastrophically. And it all sort of flows, all the gas flows into the center. And it will conserve angular momentum to some degree, but you end up with these slowly rotating massive spheroids. You still have a disk component, it is, rotating. But too much stuff piled up in the center because we weren't actually heating up the gas correctly, appropriately to stop it from losing this angular momentum catastrophically and flowing into the center. And you can go forward in time, over 15 to 20 years after that, with improvements in hardware, improvements in software algorithms. You can see the work of Abadi et al. 2003 and Governato et al. 2007. So you're only going back sort of 15 years or so, and things did improve a little bit, but there's still this fundamental mismatch. There's still way too much light tied up in the bulge spheroid component. Nothing that really looks like a grand design spiral arm in the right direction, but we hadn't got anything really that looked like a Milky Way or an Andromeda style galaxy. Where the field really changed, came along. I'd like to take credit for it, but it was more my postdocs and students who were driving this work. This work really got 2010, 2011. So we're looking about 10 years ago. So this was the first successful late type galaxy, not like grand design one like the Milky Way, a much smaller one, a dwarf galaxy, but it was the first successful one that effectively was bulgeless, or had just a tiny amount, 4% of the light was tied up in the bulge, rather than the enormous bulges and spheroids that had existed in every simulation up until that point in time. Some of it was just getting very high resolution. It allowed us to resolve more of the physics that in the previous simulations could not be resolved. It allowed us to probe high density gas regions where stars actually form with a bit more physical justification. So that is part of it. It allowed us to resolve the interstellar medium more accurately. It allowed us to track the gas flows as explosion energy pushes gas through this inhomogeneous interstellar medium. It allowed us to remove some of that low angular momentum gas that would otherwise have just piled up in the center, that stopped the formation of these central bulges. It stopped all of this low angular momentum gas dragging in dark matter and giving you a central dark, really high density dark matter core. The way in which we did that was we really made use of an enormous amount of energy from the exploding stars, the supernova, with roughly about half of it going into thermal energy to heat up the surrounding interstellar medium. Previous simulations, not only were they lower resolution, but they had worked under the incorrect assumption that most of the energy from an exploding star would get radiated away without actually interacting with the surrounding interstellar medium. We recognized that that was not going to be the case, and so we tapped into some of that energy, say about 40% of it, for every exploding star went into heating up in a thermal sense the surrounding interstellar medium. If you get into the gory details, and then so the top left panel looks at the rotation velocity of the simulations. The one which has the highly peaked rotation curve in the center is what happens when you don't heat up the gas appropriately and all the low angular momentum gas piles up and you get this fast rotating inner core. The other simulations, the bottom four, which have more or less flat rotation curves, the thermal energy that went into heating up the surrounding gas stops all of that low angular momentum gas from piling up in the center, which gives you these flat rotation curves, which is what you actually observe in nature. You don't observe these highly peaked rotation curves in the inner bit. You observe flat rotation curves. So it suggests that we're working in the right direction. Top right panel shows the density of the dark matter as a function of radius. If you don't have strong feedback, you end up getting that dash curve at the top. So the low angular momentum gas piles up in the center and it drags dark matter in with it. And so you get these dark matter cuspy profiles where it piles up in the center. By keeping that gas from dragging in the dark matter, not only do you get a flat rotation curve on the left, but you get this flat core in the dark matter density distribution, which again is what you actually observe in nature. And then the bottom panel, you can see the distribution of the light as a function of radius, and it's more or less just a pure exponential disk with just a tiny bit. But like I said, about 4% of the light is tied up in this bulge in the center. And that was the first time anything like that had been seen. So it got a lot of attention. It was sort of a feather in the cap of the team. But you don't get something for nothing, and we spent the next few years digging around in those simulations, trying to find not so much where they worked, because it was fairly clear where they worked, but trying to identify where they didn't work. And so there were a couple. I'll just point out two very quickly that came to us very quickly thereafter, where there were some problems. So the top left panel shows you the kinematics of the cold interstellar medium, the gas inside of these simulations. It's the velocity dispersion of the gas. And in nature, you get these the curves that are at the top. So the velocity dispersion as a function of radius is sort of between 10 and 15 kilometers per second. Our simulation, even though it fixed a lot of the problems and was the first to be bulgeless and etc., but one of the problems was the interstellar medium was too kinematically cold. Basically, the gas in the end was moving around, just marching around in lockstep in perfect circular orbits, without sort of bobbing around, without having any turbulence. So we ended up, you can read off the bottom there, it's between sort of 1 and 2 kilometers per second is the velocity dispersion, which is, about an order of magnitude lower than what you observe in nature. So yes, it fixed some problems, but we ended up getting this rigidly rotating, inflexible interstellar medium, which is not what you actually observe in nature. And despite our best efforts to stop it piling up in the center, top right panel shows the yellow horizontal line is the upper limit for cold interstellar medium in nature. in surface density units. The details don't matter. But the curves, the points above it, are our best simulations. So yes, it is more distributed. It didn't pile up in the center in the same way that the earlier generation of simulations did, but we still have too much gas in the inner part of the galaxy, higher than the empirical upper limit that you see in nature. So yes, we fixed a lot of problems, but it was also pretty clear that there were still some issues, particularly in the gas physics. So what we've been doing, what we did subsequent to that, was fine tune that first bulgeless disk simulation. Spent a number of years going through large parameter surveys, trying to optimize how we extract energy from exploding stars, how we extract energy from stars before they explode, making use of the radiation that comes off of the star before it ever explodes, doing things like improving the way in which metal diffusion works, and I will mention that right towards the end in terms of some of the outstanding bugs, and a number of other issues related to star formation thresholds and various other things like that. At the end of the day, what it came down to was just maximizing energy feedback. So whether it's maximal feedback, strong feedback, different terms that people have used, but really, at the end of the day, what it was it is the feedback that you need to actually ensure that you get a good representation of a galaxy. Probably it all came to a head in this paper for us, this collaboration that I was involved with called MaGICC, Making Galaxies in a Cosmological Context. Don't expect you to go wading through all of these. These are just 8 different what we call scaling relations for galaxies. I'll just pick out a couple of them. For example, the one on the top left is relationship between the stellar mass and the total dynamical mass of the galaxy. In the red band across is what you observe in nature, and the 6 yellow and green diamonds are simulations where we worked hard on the parameter study to get the best looking galaxies that we could. The red triangle off by itself is what happens if you do not take care and try to use the strong or maximal energy feedback. You can look at the panel beside it is the log of the rotation velocity against the luminosity of the galaxy. It's called the Tully-Fisher relation. There's bottom left is size, rotation velocity. Over on the right, the right panel, you've got top. Let's see. I don't know. The bottom right is the metallicity of the gas versus the mass in stars, and the yellow and green in each panel are simulations, and the various black curves and dots and etc. are the observations. And what you can see without spending a whole lot of time is that those strong feedback runs in yellow and green are all consistent with these 8 different scaling relations. And the ones that are the red triangles or red diamonds are what happens when you use conventional feedback and don't use the maximal energy feedback. In some scaling relations, it doesn't make a difference, but then in other scaling relations, it makes a big difference. And so this was the first suite of simulations that actually looked at all 8 scaling relations simultaneously, unlike anything that had been done previously. So this was pretty good. And if you take a step back and forget scaling relations and just look at what the simulations actually, to the eye look like, this is kind of the state of the art. In that panel there's 6 simulated galaxies and 6 just drawn from astronomy picture of the day. And by eye, even the experts, you can't tell which are the real ones and which ones are the simulated ones. And so this, when that was that's 8 years ago when that work came out. That was the first time people could look at simulated galaxies and not put hand on heart and know for sure whether it was a real one or not. Doesn't necessarily make them right, because as I said, we already knew that there were some problems, in particular with the interstellar medium. But at least if you just did a quick eyeball look of them, we were, go back to one of the very first slides that I said at the beginning of the lecture. Do we actually have simulations that look like real galaxies? If you're going to data mine those simulations, you want to at least know that they look like a real galaxy before you try and tease out any of the underpinning physics. But we're now at a stage, it took up until, only 8 years ago, but We now have galaxies that look like real galaxies that fill you with some confidence that let's dig into them, let's see what works, what doesn't work. You can come up with an entire shopping list of the sorts of things that you might want to dive into in these simulations, and they're exactly the same shopping list you would if you're an observer, in terms of going out and looking at the distribution of stellar light, age gradients, abundance gradients, the relationship between age and metallicity. If you're interested in the gas, it might be super bubble size distribution, structural power in the interstellar medium, surface density profiles, velocity dispersion profiles, which I've already alluded to. There's lots of things that you can do. We've done some of them. A lot of these are still things that are work in progress. It's just people power limited in terms of getting people working on these different things. Um, I'll delve into just a couple of them sort of over the last 10 minutes or so, just to show you where things stand. Just a few more words on how we actually set the subgrid physics right to get those galaxies to look nice. Like I said, the answer comes down to feedback, and how you take the energy from supernova in particular and couple it to the surrounding interstellar medium. And what it really boils down to is it's a number of efficiency factors, because again, we're not resolving that physics. It's orders of magnitude below the resolutions that galaxy simulations work at. So you have to put in fudge factors, efficiency factors, however you want to phrase them, that capture this unresolved physics. And their efficiency factors related to the rate at which you convert gas to stars, star formation efficiency. You've got the energy feedback efficiency. And there's a few other ones as well in terms of heating from supermassive black holes. Lots of other ones as well. So how do we actually do it in nature? There's three major groups, at least up until a few years ago. There's more now that are working in this field. There was our group, MaGICC. There's much bigger groups across Europe, which is Eagle, and a much bigger group in the US called Illustrious. But the one common calibrator that is used for all of these different groups is one that I alluded to a couple slides ago, is this relationship between the stellar mass and the halo mass, M star, M halo relation. So here it is, just zooming in. On the y-axis is the stellar mass. On the x-axis is the halo mass, or the dynamical mass. The sort of the band and the line cutting across from the bottom left to the top right is what you observe in nature. All of the little colored, you've got diamonds and squares and plus symbols and triangles, etc. Those are all the simulations that existed up till circa 2010 or so. And what you see is basically all of them sit for a given dynamical mass or a given halo mass. They form too many stars by factors of few to an order of magnitude. So they get the wrong baryon fraction, or the wrong stellar mass fraction. What it really means is that gas had a tendency to pile up in the center, and when gas gets dense, it forms stars, and so you get this runaway process of just forming too many stars. You form them in the wrong place as well, but overall you just form too many stars. So all the simulations up to 2010, like I've just been talking about a few minutes ago, all had the wrong baryon fraction. And so what we did was we took one of our simulations, just one of them, and worked out what is the star formation efficiency that we need to place one galaxy, which is that yellow diamond, on the observed relationship, the stellar mass halo mass relation. And the details don't matter, but it roughly was about a 3% efficiency. So whenever the gas got dense enough to form stars, about 3% of that gas went into forming stars. That was wasn't 4%, wasn't 8%, wasn't 1%, but 3% was the number that we needed in terms of efficiency, and it was not wildly dissimilar to theoretical predictions as to what you would need. Having tuned, if you like, one simulation to fit on one scaling relation, we then applied that to the other 5 simulations that I mentioned. And so again, that top left panel that you see there again is stellar mass halo mass relation. And having fixed one galaxy onto one scaling relation, the other 5 all naturally fell onto it over sort of a couple orders of magnitude of dynamic range and stellar mass. That was good. We didn't have to tune the other galaxies to get them on there. The other ones least over that dynamic range, naturally fell onto the relationship between stellar mass and halo mass. And more importantly, those 6 galaxies sat on all the other 7 scaling relations that you can see in those 2 panels. There was no fine tuning to get them to land there. They all worked out naturally. Having tuned one simulation on one scaling relation, everything worked out. So there's, a nice feeling of confidence that we'd sort of captured the physics correctly, at least at the resolution that we were running at. Now, if I take a step back and look at the other 2 competing groups, Illustris and Eagle, much bigger groups, and nowadays have access to much bigger facilities. Their approach was not to just calibrate on one scaling relation, which is our approach, the stellar mass halo mass relation. Illustris and Eagle also calibrated on that one, but you can see from the bullet points there that they've also simultaneously calibrated on other scaling relations, ones that we didn't even look at. So in the case of Illustris, yes, they tuned to make sure they recovered the stellar mass halo mass relation, as we've done in some sense. But they also ensured that the relationship between this star formation rate as a function of look back time through the universe, or redshift, was also covered, was calibrated upon. Eagle went one step further, well, 2 steps further. They've got 1, 2, 3, 4 scaling relations that they have calibrated on: stellar mass, halo mass, the mass function, the relationship between size and stellar mass, and the black hole stellar mass relation. So it wouldn't be shocking to say, if I put up the relationship between star formation and redshift, we didn't calibrate on it, so there's no guarantee that we would recover it perfectly. Similarly, Eagle didn't calibrate on star formation rate against redshift, so theirs may not match perfectly. It might not. Illustris, if they show you a plot of star formation rate against redshift, of course it's going to look good because they calibrated their model to make sure it recovered it. And similarly, like I said, Eagle calibrated on 4 different scaling relations. So the fact that they get the size against stellar mass right, it shouldn't shock you if they showed you that plot, because they have fine-tuned their simulations to make sure that they do recover it, whereas both our team and the Illustris teams didn't calibrate on that, so there's no guarantee that we would actually recover it. So it really depends on who's sitting here giving you a talk about their work. So for example, it's a bit busy here, but if you look at the plot on the left, that's what we call the mass function. It's a logarithmic distribution of the number of galaxies as a function of stellar mass. You'll see all the curves, they're higher at low mass, because low mass galaxies are much more common than high mass galaxies. Now, if you look at the observations are just in, what is that, sort of pink and green, and the red and black lines are the Illustris simulations. Now, the simulations overproduce the number of low mass galaxies. They also overproduce the number of high mass galaxies, and they get it right sort of in the middle. But again, the stellar mass function was not one of the scaling relations that Illustris calibrated on. So while they will get star formation rate redshift correct, because it was one of their calibrators, they don't necessarily get the mass function right, because they didn't force their simulations to be calibrated to that. So it's not shocking. Similarly, Eagle has calibrated on 4 different things. They will get the mass function right because they forced their simulation to recover it. But they didn't force their simulation to recover the relationship between star formation rate and redshift. So they've got, which is the bottom right panel, their simulation is the solid black curve. It's got roughly the right shape from the observations, but sits about a factor of 2 low. So again, not shocking. The Illustris will recover it perfectly because they force their simulations to do so. Eagle does not, because that was not one of the calibrating scaling relations that they looked at. So, the devil is in the details there. Similarly, I guess this panel down here shows the relationship between the mass of the system and how much gas is enclosed. And This is for the Eagle simulations, the European-based ones. Observations are all the open triangles and plus symbols and asterisks. And the filled circles are their simulations. And what you can see right away is that the simulations in blue, the reference simulation, again, all sit high relative to the observations. And that's simply because Eagle is calibrated on 4 different scaling relations, but the amount of gas, the relationship between gas and halo mass is not one of the things that they calibrated, so they've got too much gas sitting there at the end, which would also explain why their star formation rate sits low, because they've not converted gas into stars at the appropriate rate. So just to wrap up, just to go through a couple of things on our simulation side, what works, what doesn't work, and then just touch on one hidden numerical gremlin, which is something called diffusion. First, what are some of the good things that work in the simulation? Well, broadly, how the chemical abundances are distributed has actually worked out really well. If you look in the top right is a ratio of magnesium over iron as a function of the iron abundance. What I want you to take from that is there are basically 2 almost parallel tracks. The one at the bottom relates to the ratio of magnesium to iron in the stars that are close to the have the same kinematics as our sun, what we call the thin disk stars. And then there's a parallel track which is enhanced, which are called thick disk stars, which are older and have slightly different kinematics. And this is what you observe in nature, and there's this roughly factor of 2 offset between the two. That is a very important diagnostic of the star formation history of our Milky Way. It tells us that they're in the distant past, probably 12 gig years ago, there was a break, cessation, a hiatus in star formation, with the thick disk forming first, then a hiatus, and then the thin disk continuing to form thereafterwards, but at a lower ratio of magnesium to iron. And one of the first simulations that we looked at of ours is shown below. It is not meant to be a one-to-one faithful reproduction, but there is sort of, if you defocus your eyes, you can see that there are 2 sequences that are offset from each other. And the kinematics of those stars, the one at the bottom is the thin disk, the one at the top is the thick disk. Again, not a one-to-one match, but the hiatus in star formation, the dip in the star formation in the simulation, which you can see to the left, where the red arrow was pointing, that dip there corresponds to where you get the break in the trend. So we captured inside of the simulation, without trying to, features that look like the chemical features in the Milky Way. If you take one of our more recent simulations, it looks a little bit it's a little bit clearer, the offset in the sequence between the thick disk above and the thin disk below. So again, reassuring that without setting out to capture that thick and thin disk chemical abundance differences, we've actually captured it. One that we're looking at sort of right now is the relationship between those chemical ratios of magnesium and iron as a function of age. And as you move to the right in that panel, that's older stars, and the ratio goes up. On the left is younger stars, the ratio goes down. That trend in the ratio of magnesium to iron, again, is a good diagnostic of star formation timescales that are occurring. And all of those symbols that you see there are observations. If you take one of our simulations from a couple of years ago, Leah Cox is working on now as part of her PhD here at Hull. That's what the sort of snaky black dots that you see going across the bottom right panel there is the ratio of magnesium to iron as a function of age inside of that simulated disk, grand design spiral. And the symbols with error bars on them in that plot are the observations that you see over on the left. And then the various curves there are analytical models that Kate Womack is working on as part of her BSc project here. So that, again, this is a reassuring thing, that relationship between these chemical elements as a function of time has been captured naturally inside of these simulations without going out of our way to try to force it, which is, again, reassuring. One of the things that doesn't work so well, and it's one of the challenges, I guess, for these sorts of simulations, is metal diffusion. Now, these are particle simulations, and particle simulations are exactly what they sound like. Gas particles are particles. Now, um, those gas particles have temperatures, they have chemical abundances attached to them, but a particle is a particle. Unless you tell the particles as they go past each other, you may have a hot particle and a cold particle. Unless you tell them how to diffuse the heat across from each other, they will carry that heat and they won't share it. Similarly, one particle may have a lot of metals and another particle may have very little in the way of metals. But they're fluid particles, they're gas particles. So if this was nature, you take fluids or gases and mix together and they share that information. In these simulations, these particle-based simulations, they don't. Unless you tell those particles how to diffuse information across from each other, they won't share that information. So the top right that you're looking at there is a relationship between the metal content as a function of age in a simulation where we turned off diffusion. So at any given age, there's a whole wide range of metallicities. So the scatter at any given age is quite large because you've not allowed any of the metals to diffuse from particle to particle when they're near each other. Then on the left is a simulation where the diffusion was cranked up, and you bring the scatter down dramatically as you allow gas particles to share information very quickly in that sense. There's lots of mathematical underpinnings there with shear tensors, pairwise velocity differences, turbulence models. But at the end of the day, it's still not something that you can formulate from first principles with a whole lot of confidence. It is something that does need to be calibrated, and it does make a huge difference in terms of how metals get distributed, depending on how you treat that diffusion. And it's something that is, with these smooth particle hydrodynamics approaches, that it's usually sort of swept under the rugs. So it's slightly worrying, let's say. Another thing that actually works out pretty well is how metals are not distributed in a particular region, but how they're distributed across the entire galaxy, what we call the metallicity gradient. And sort of like complicated plot, but on the y-axis is the gradient into the metal content and how it varies as a function of position. So in this case, it's log scale. So 0.3 is a factor of 2 difference in the metal content for every kiloparsec that you step out through the disk. So a big negative number means a steep metallicity gradient, and a value near 0 would be a flat metallicity gradient. And on the x-axis is redshift, so the distant passes on the left and today is on the right. What you see is there's 2 suites of simulations there. There's 2 curves near the top, which are the simulations I've just been describing with strong feedback. Strong feedback pushes metals around more or less all the time and keeps the metallicity gradients fairly flat. Weak feedback, so the green curves that are dipping down to the bottom left. Weak feedback means gas piles up in the center, and the metals also stay around the center, which means you get steep gradients, particularly at early times. And the various symbols that you see there superimposed are different observational data sets. The main thing to take from that is that at low redshift, or today, the models all are degenerate. So looking at the metallicity gradient today doesn't tell you whether feedback was strong or weak because the models become degenerate. It's only when you push back in time that you see some galaxies have steep gradients, some have flat gradients, which tells you that strong feedback works really well for a lot of galaxies, but there are some galaxies at high redshift which have very steep gradients, which would suggest that at least at high redshift, feedback was not particularly strong. So this is an important signature of galaxy formation and evolution that really wasn't recognized until we started digging into these simulations about 8 years ago. Another thing which is actually works out pretty well is, and it's not something we'd really thought about at the time, um, everything I've talked about now is gas and stars that are inside of the disk of the galaxy. But as you have strong feedback, you can actually have feedback that is so strong that it drives metals out of the disk and up into the halo surrounding the galaxy, what we call the circumgalactic medium, the CGM. And what you can do in nature is, if you're lucky, if you've got a distant supermassive black hole, a quasar on the other side of the universe, shining its light that happens to punch a hole along its pathway towards us through the halo of a galaxy, you can measure various ionized species of oxygen and magnesium and various other chemical elements. Um, and with a large enough sample, you can figure out how many metals there are away from the disk up in the circumgalactic medium. And that's what the figure that's shown there, the green and blue, are observations of oxygen 6, so 5 times ionized oxygen, way out into the halo of various galaxies. And the different black locuses, gray locuses there are observations. The main thing to take is when you look on the two left panels, the simulations are several orders of magnitude below the observations. That's what happens when you get weak feedback. And when you've got strong feedback, which works for so many of the scaling relations that I just talked about, without fine-tuning or doing anything, you can see the simulated data goes right through the observations, which again gives you some degree of confidence that the feedback that we implemented has actually been captured correctly, not just because it gets all the scaling relations for the gas and stars inside the disk right, but it actually gets the circumgalactic medium right as well. And the last thing I want to finish on is less about the physics of the simulations, the maths of the physics involved. It's just how we actually look at the simulation, and that's broadly, are we analyzing the simulations correctly? Are we actually doing a fair comparison with, in the same way that observers are looking at observational data? Now, I've used the word star particles loosely, but these aren't individual stars. We don't resolve individual stars. Our galaxy has 100 billion stars, maybe 200-300 billion stars in it. We're not running simulations at that degree of resolution that we capture individual stars. We might have, say, a million star particles inside of our simulation. What that means is that each star particle, if you like, is on the order of several thousand or 10,000 times the mass of the sun, or you can think of it as every star particle really is about 10,000 stars. So this is the question. Are we analyzing these simulations correctly? So if you took, say, a few 100,000 stars from a cluster in nature, an open cluster, say, or a globular cluster, and I plotted them in this plane of color on the x-axis and brightness or magnitude on the y-axis, this is what 100,000 stars would look like. And it's not just some random distribution of points. There's structure in there, the big black curve going cutting across a swath there. There's hydrogen burning in the core. The thin one that heads up to the top right is the giant branch, where you've exhausted hydrogen burning in the core. You're burning hydrogen as shell around the core. The one way down at the bottom left would be remnants, white dwarfs. The future for our sun in 5 billion years would be to shift down into that locus of points down there. But that's what would happen if you grab 100,000 stars from a cluster in nature. That's what it would look like. But for us inside of simulators, those 100,000 stars actually look like this. It's an individual star particle. And so I guess the broader question is, is stacking up a whole bunch of these things which hide an enormous amount of information in one single point. The same thing as taking a distribution of millions of stars in nature, here plotted as, again, brightness on the y-axis and color on the x-axis. This is how observers would do it. They would take distributions of millions and millions and millions of stars and then pick out the stars that they're really interested in analyzing. So for one survey that I've been involved with, the Gaia ESO survey, that little blue box is the stars that we selected to actually analyze and look at things like the chemical composition, etc. Inside of my simulation, I'm not picking out those individual stars. I'm picking out those composite star particles, if you like, rather than individual stars. And so, if you take effectively every paper in the field, 99.99% of them, pick up those composite star particles, that one dot that you see there on the left, and compare those, even though that's really 100,000 stars hidden inside of that one composite particle, what I end up doing is comparing those composite particles against individual stars. So whenever I make a plot, and I've shown you some of these plots already, it could be the top two are the distribution, it's a histogram of the taking stars in the solar neighborhood and looking at their metal content. The middle panels are one that I showed you just a few minutes ago, which is metallicity on the y-axis against age. Those trends tell you, again, something about the formation history of stars in the solar neighborhood. But each of those in nature are obviously individual stars, and inside my simulation, these are composite particles that have 100,000 stars hidden inside of them. So I just look at one particular problem, which is the metallicity distribution function, which I mentioned just a second ago. Again, just a histogram of the number of stars that sit in each metallicity bin. And this is a weird logarithmic scale where 0 means it has the same metal content as the sun. A value of -1 means it's 1/10 the metallicity of the sun. -2 means it's 1/100th the metallicity of the sun. And this is just taking, several hundred stars in the neighborhood of our sun and showing you what the distribution of the metal content is for those stars. And so you could look at that distribution function and you could measure things like, okay, what is the mean? What is the dispersion? If it was a nice perfect Gaussian, you just report back the sigma. It's not a perfect Gaussian, so you can measure things like the skewness. You can measure their kurtosis to see how much it deviates from a pure Gaussian. So there's lots of things you could measure, and you can do exactly the same thing in the simulation. And that's what we did. We went off and ran a bunch of simulations. We went to the solar neighborhood of the simulations. We made those same metallicity distribution functions, and we did exactly that. We measured the skewness. We measured their kurtosis. And what I want you to take from these numbers that I put the box around is not to memorize the numbers. That's not important in the slightest, but just to note that when I look at skewness, you can see a range from, depending on what type of physics I put into my simulation, what type of subgrid physics I put in, what the sort of feedback that I put in. Do I turn on, how do I treat diffusion? There's lots of different physical models in there. Again, each one doesn't really matter, but you can see the skewness and the kurtosis varies. That distribution function will change depending on the subgrid physics, the actual physics I put into my simulation impacts on those distribution functions. Now, what I want to do is I want to take those composite star particles in my simulation and try to turn them into real stars so that I can select my stars the same way that the observers do. Now, what I can do is that for each one of those star particles, I do know the age of that star particle. I know when it formed. I know what its metal content is. And I know what the relative distribution of stellar masses are inside of that 100,000 solar mass particle, if you like. I know how many 100 solar mass stars there are. I know how many 50s and 20s and 10s and 8s and 5s and 4s and 1s and 0.1s, etc. So what that means is I can take that thing and I can blow it up into individual stars using what we call isochrone stellar evolution models, sorts of things that Marco Pignatari and his team here at Hull work on. It allows me to populate, in terms of a plane like luminosity against temperature or luminosity against color, how many stars sit in each particular bin, and it's called creating a synthetic color magnitude diagram. And that's exactly what we did. We took our simulations, we placed ourselves inside them at the position of where the sun would be, if you like, the solar neighborhood, and then selected stars, individual stars, in exactly the same way that observers would do, by taking those composite star particles inside of the simulation, I know how far away they are. I know the age. I know how many stars of individual mass are inside of that particle. I know the metal content. And so I can blow up those particles into individual stars, and then I can select them based on the same color and luminosity cuts that observers would do. We did 2 tests, and I'll just show you the results very quickly. This was the first one. First one a few years ago. My student Maida, she took one of our simulations, blew up the particles into individual stars, and then that allowed her to do something that people in this experiment called RAVE, radial velocity experiment. They selected all stars with an infrared brightness between 9 and 12. And so that, which is what, when I take the composite star particles that you see in the panel to the left, the top left, and I put them into a infrared versus visual minus infrared, the bottom right panel, the white horizontal bars are what the observers would select. All of the stars that lie between 9 and 12 went into the radial velocity experiment, and those are the ones that they generated metallicity distribution functions for to measure skewness and kurtosis for just the stars that lie within that apparent brightness band. I can do other things as well. I can look at stars that are burning hydrogen in the core, which is the bottom left panel. I can pull out stars that are no longer burning hydrogen in their core, just burning hydrogen in the shell around the core, which is the giant branch stars. So I can slice and dice my simulation to bring it even closer to the sort of the star selection that is done by the RAVE experiment. And so if I boil it down, that thick black curve that cuts across is the metallicity distribution function if I just take the star particles from the simulation. And so again, the numbers don't matter, but if you look at the top right of that panel, you see skewness minus 1.5, kurtosis 2.5. If I were to take the, got that one mixed up. The thick black lines, those are the simulation particles. So if you look at the bottom left, skewness minus 1.2, kurtosis 1.4. If I were to, again, don't need to memorize the numbers, but if I pass it through the synthetic color magnitude diagram tool, pick out stars that are between 9 and 12, the same way the observers did, then I get what you see in the top right, which is the synthetic cut. So the skewness goes from minus 1.2 to minus 1.5. Kurtosis goes from 1.4 to 2.5. If I just select hydrogen burning and non-hydrogen burning stars, which is what the red and the blue are, you can see now how the numbers change. And again, the individual numbers aren't what is important here. The main point is that simply by choosing stars correctly, the same way observers do, rather than just taking the composite star particles, which is the way that all simulators do, I can change the measured skewness and kurtosis, the distribution of metals in my solar neighborhood, at the same level as all of the gory subgrid physics that people have spent the last 40 years fine-tuning things related to feedback and star formation density thresholds. Just how I look at the simulation can be just as important as the actual underlying physics. And this was something that was not appreciated until this paper. And the last one I'll show you is just a more recent work that we've done in 2018 using a slightly more sophisticated survey, the Gaia ESO survey, which was not just selecting stars between 9 and 12 in the infrared band. It uses a much more complicated selection function, also in the infrared, but fainter stars, more distant stars. It also makes a color cut. And it also looks at the surface gravity of the stars and only chooses stars that are just starting to exhaust their hydrogen burning in the core, because that gives you a good measure of the age in theory. It basically boils down to that blue box that you can see on the screen before. And so we went through the same process, selected, went inside of our simulation, pulled out the composite star particles, we blew them up into individual real stars using synthetic color magnitude diagrams, and selected stars that fit within that selection function that we used in the Gaia ESO survey. The only test I'll show you is what happens if I not look at the metallicity distribution function, but I look at the age distribution function. So I choose the stars that made it pass through that selection function and look at the distribution of the ages. If I took the composite star particles straight from the simulation, um, then you would get the blue histogram that you see there. So a modal age of around 8 billion years. Now, if I take the simulated star particles and blow them up into individual stars, and then select the stars the same way that we did in the Gaia ESO survey, then you would get the red curve. And so you can sort of see the red histogram, the modal age is around 4 billion years. So I've gone from basically what a simulator would tell you is the age of the stars in your sample, which is the blue curve, 8 billion years, to bringing it closer to the observer's plane. And I would then report that the mean age is more around 4 billion years. So, it's 4 billion years difference just on, again, how I look at the simulation. So it can make things quite substantially different. And it comes into play. I mentioned Leah Cox's work that she's doing. Part of her thesis is looking at the distribution of ages in simulated halos, not the disks that I've been talking about thus far, but the halos of galaxies, and comparing them with what you see in the Milky Way. In the Milky Way, you see this distribution here. Red is younger, blue is older in this particular panel. And so as you move to the outer part of the Milky Way's halo, it's about 1.5 billion years younger than the inner part of the halo. Again, there's telltale signatures in there that about how the very first epoch of star formation occurred in our galaxy and how the halo assembled, how much of it was assembled versus formed in situ. And this is work that she's doing on. But the main point here is that I've just told you how I look at the simulation can have changes in the interpreted ages of billions of years. And if you're interested in teasing out the formation history of the Milky Way's halo, where you're talking gradients of 1 to 2 billion years, again, how you observe that simulation can be much bigger than the sorts of things that you're trying to tease out of the simulation itself. So you have to observe the simulation as carefully as possible, otherwise you're going to get results that are not necessarily correct. So again, this is a big part of what Lee is working on right now. So I have no magical summary to pull it all together. I think hopefully you've enjoyed the walk through the history from the 1840s through to the very first simulations, why they didn't work up until maybe 10 years ago or so, and how a careful accounting of the feedback energy from exploding stars and coupling that to the surrounding interstellar medium is the dark art in all of this field, and sort of have maybe a slight appreciation for the contributions that we made sort of the 5 to 10 years ago period to really form those first truly grand design late type bulgeless disk galaxies, which has now become the industry standard way of doing these sorts of simulations. And to me, maybe the most important thing really is this little summary is, how you observe your simulation can be as important as all of the subgrid physics that I spent a whole lot of time talking about. So hopefully you pick something up along the way. If you have any follow-up questions whatsoever, please get in touch with me. If there's some time, maybe we'll run a little online chat, like I said at the beginning. But in the meantime, wish you guys all the best for upcoming exams, for projects, and hopefully once all this nonsense is passed, we'll have a chance to sit down and share a pint or two and talk about what we've been up to over the last few months. So take care. I'll talk to you very soon. Cheers.